Tonight, we're going to talk about size. Not the size of a building, not the size of a mountain, not the size of a planet or a star or even a galaxy. We're going to talk about the largest structures that physics allows to exist. Objects so enormous that the word enormous becomes meaningless before we're halfway through the list. Objects so large that light itself, traveling at 300,000 kilometers per second, takes millions and billions of years to cross them. Objects so vast that our entire galaxy, 400 billion stars, 100,000 light years across, would be an invisible speck floating inside them. And we're going to do this in order. We're going to start with the large and work our way to the unimaginable. Each step up the scale will make the previous one feel small. Each new object will redefine what your brain thinks big means. By the end of tonight, your sense of scale will be permanently altered. And I mean that literally. The way you think about space, about distance, about the universe you live in, will not be the same after this. There is also something at the very end of this list that breaks the rules. A structure so large that it technically should not exist, according to our best cosmological models. Something that challenges one of the foundational assumptions of modern physics. And the fact that it exists anyway tells us something important and unsettling about how much we still don't understand. By the end of tonight, you're going to understand what the largest things in the universe are, how they formed, what they're made of, and why the biggest of them all is a problem that cosmologists are still arguing about. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Before we start climbing the ladder of cosmic size, we need to establish where we're starting from, because the objects we're going to discuss are so much larger than everyday human experience that without a baseline, the numbers become meaningless noise. You, right now, wherever you're watching this, you are approximately 1.5 to 2 meters tall. That's our starting point. One human being. The Earth has a diameter of approximately 12,742 kilometers. That's about 6.4 million times taller than you. If you lined up 6.4 million people standing on each other's shoulders, they'd reach from one side of the Earth to the other. The Earth is large, but the Earth is not large by the standards of what we're discussing tonight. The Earth is a dust particle. The Sun has a diameter of approximately 1.4 million kilometers. That's about 109 times the diameter of Earth. If the Sun were a basketball, the Earth would be a marble. If you hollowed out the Sun, you could fit approximately 1.3 million Earths inside it. The Sun feels enormous when you think about it from Earth. 8 light minutes away, dominating the solar system, maintaining the orbits of 8 planets through its gravity. But the Sun is a perfectly average, unremarkable star. There are stars that make the Sun look like the Earth looks next to the Sun. The distance from the Sun to the nearest star, Alpha Centauri, is approximately 4.24 light years. That's 40 trillion kilometers. That's the distance light covers in 4.24 years at 300,000 kilometers per second. Our fastest space probe, Voyager 1, would take approximately 73,000 years to cover that distance. 4.24 light-years is the gap between neighbors in our cosmic neighborhood. It's essentially empty space between 2 points of light. The Milky Way galaxy has a diameter of approximately 100,000 light-years and contains roughly 400 billion stars. The distance from one edge to the other is 25,000 times the distance to Alpha Centauri. The light from a star on the opposite side of the galaxy takes 100,000 years to reach us. The Milky Way is a structure of breathtaking scale. And the Milky Way is where we begin, because everything on tonight's list is larger than the Milky Way. Some of them are larger than thousands of Milky Ways. Some are larger than millions. Let's start climbing. Before we get to structures made of many stars, let's establish just how large a single star can get. Because the range of stellar sizes is itself almost incomprehensible, and understanding it sets the stage for everything that follows. Our Sun, as we said, has a diameter of 1.4 million kilometers. It's a perfectly average G-type main sequence star, yellow, stable, middle-aged, unremarkable by galactic standards. Approximately 70% of all stars in the Milky Way are smaller than the Sun. Red dwarf stars, which are the most common type, range from about 10% to 50% of the Sun's diameter. They're dim, cool, and extraordinarily long-lived. The smallest red dwarfs will burn for trillions of years. But on the other end of the spectrum, stars can get far, far larger than the Sun. Massive stars, blue giants, blue supergiants, can have masses of 10, 20, 50, even over 100 times the Sun's mass. These stars are extraordinarily luminous. A star of 100 solar masses can be 1,000,000 times more luminous than the Sun, meaning it emits 1,000,000 times more energy per second. But it pays a price for that luminosity. It burns through its fuel at a catastrophic rate and lives for only a few million years before dying in a supernova. The Sun will live for 10 billion years. A star of 100 solar masses lives for perhaps 3 million years, less than 0.03% of the Sun's lifespan. But the truly extreme objects are not the massive blue stars. The truly extreme objects are the red supergiants and hypergiants. Stars that have evolved off the main sequence and expanded into enormous, cool, luminous giants. The largest known stars in the Milky Way and nearby galaxies are objects that defy intuition. Scuti, a red supergiant in the Milky Way, was for years considered a candidate for the largest known star. Its radius is estimated at approximately 1,700 times the radius of the Sun. If you placed Scuti at the center of our solar system, its surface would extend beyond the orbit of Jupiter. The orbit of Jupiter, a planet 5.2 times farther from the Sun than Earth, would be inside the star. Stephenson 2-18, another candidate for the largest known star, has an estimated radius of approximately 2,150 solar radii. If it replaced the Sun, its surface would extend almost to the orbit of Saturn. Saturn, the sixth planet from the Sun, entirely inside the star. Canis Majoris, a red hypergiant, has a radius estimated at around 1,400 to 2,000 solar radii depending on measurement method. It's so large that if you traveled around its equator at the speed of a commercial airplane, the journey would take approximately 1,100 years. But even these enormous individual stars are just points of light in the context of what comes next. A red hypergiant with a radius of 2,000 solar radii has a diameter of approximately 2.8 billion kilometers. That's 2.8 billion kilometers across. Impressive for a single object, but the structures we're about to discuss make even this seem trivial. Because those structures contain millions, billions, and trillions of stars, just like this one. The next rung on our size ladder is the nebula. Not a single star, but vast clouds of gas and dust that span light years or hundreds of light years. The environments where stars are born and where they leave their remains when they die. Nebulae come in several types. Emission nebulae are clouds of ionized gas lit from within by hot young stars. The Orion Nebula, about 1,344 light-years away, is one of the most photographed objects in the sky, and it spans about 40 light-years. 40 light-years of glowing gas and dust, containing hundreds of young stars still forming, stellar nurseries where planets are currently coalescing from disks of material around newborn suns. Reflection nebulae. Like the Pleiades star clusters surrounding haze, scatter the light of nearby stars and glow with reflected blue-white light. Planetary nebulae, misnamed because they have nothing to do with planets, are the expelled outer shells of dying stars, like our sun will become. Glowing rings and bubbles of ionized gas surrounding the hot, white dwarf remnant at the center. Dark nebulae are dense clouds of gas and dust that block background light rather than emitting it. But the largest nebulae are the giant molecular clouds, vast, cold, dense structures that are the fundamental building blocks of star formation in galaxies. The Orion Molecular Cloud Complex, which contains the Orion Nebula as just one small part, spans approximately 500 light-years. 500 light-years of gas and dust, containing enough material to form tens of thousands of stars, with active star formation occurring in multiple regions simultaneously. The largest individual molecular cloud complex known in the Milky Way is the Tarantula Nebula in the Large Magellanic Cloud, technically in a neighboring galaxy, but close enough to study in detail. The Tarantula Nebula spans approximately 1,800 light-years and contains some of the most massive stars known. It's so luminous that if it were at the same distance as the Orion Nebula, it would cast shadows on Earth at night. But even 1,800 light-years is a small fraction of our galaxy's 100,000 light-year diameter. We've barely started. Stars are not evenly distributed through galaxies. They form in groups, in clusters, in associations, gravitationally related families that were born from the same molecular cloud. Open clusters are loose groups of hundreds to thousands of young stars that form together. The Pleiades, visible to the naked eye as a tight group of blue stars in the constellation Taurus, is an open cluster containing about 1,000 stars spread across approximately 43 light-years. The Hyades, the nearest open cluster, spans about 65 light-years. Open clusters are loosely bound. Over time, interactions with other stars and clouds gradually disperse them, and most open clusters dissolve into the surrounding galaxy within a few 100 million years. Globular clusters are far more impressive. Dense spherical collections of tens of thousands to several million stars, gravitationally tightly bound, orbiting the center of their host galaxy in high elliptical orbits. The Milky Way has approximately 150 known globular clusters. The largest and most massive is Omega Centauri, containing approximately 10 million stars within a sphere about 150 light-years in diameter. That's 10 million suns packed into a sphere where the average distance between neighboring stars is a fraction of a light-year. Far denser than the solar neighborhood, where the nearest star is 4.24 light-years away. Omega Centauri is so massive, about 4 million solar masses, that some astronomers believe it may be the stripped core of a dwarf galaxy that is captured and disrupted by the Milky Way billions of years ago. The extreme density of stars in its center suggests something unusual about its formation history. It may even contain an intermediate mass black hole at its core. But 150 light-years, while impressive for a cluster, is still small by galactic standards. The Milky Way is 100,000 light-years across. A globular cluster is to the Milky Way what a city block is to a continent. We need to go bigger. Now we arrive at what most people think of when they hear cosmic scale. The galaxy. An entire system of stars, gas, dust, dark matter, and planetary systems, all gravitationally bound together, orbiting a common center, often containing a supermassive black hole at its heart. We've established that the Milky Way has about 400 billion stars and spans about 100,000 light-years. But the Milky Way, while a perfectly respectable galaxy, is not particularly large by the standards of the universe. Andromeda, our nearest large galactic neighbor, is slightly larger than the Milky Way, spanning approximately 220,000 light-years and containing perhaps 1 trillion stars. It's approaching us at about 110 kilometers per second and will collide with the Milky Way in approximately 4.5 billion years. But there are galaxies that make Andromeda look small. IC 1101 is one of the largest known galaxies in the observable universe. It's a supergiant elliptical galaxy located about 1.04 billion light-years away in the Abell 2029 galaxy cluster. IC 1101 has a diameter of approximately 6 million light-years, 60 times the diameter of the Milky Way. It contains an estimated 100 trillion stars, 250 times as many as the Milky Way. Its mass is estimated at approximately 100 trillion solar masses. If IC 1101 were centered on our Sun, its outer edge would extend more than 2 million light-years in every direction, well past Andromeda, well past the Magellanic Clouds, encompassing hundreds of satellite galaxies and thousands of globular clusters. The entire local group of galaxies, the 50-plus galaxies that make up our gravitational neighborhood, would fit comfortably inside IC 1101 with room to spare. IC 1101 formed through a long history of galaxy mergers. As galaxies collide and merge, a process that takes hundreds of millions of years per event, they combine their stellar populations, their gas reserves, their dark matter halos. The supermassive black hole at IC 1101's center has a mass estimated at about 40 billion solar masses, 10,000 times more massive than the black hole at the center of the Milky Way. 40 billion suns worth of mass, collapsed into the region smaller than our solar system. But even IC 1101, 6 million light-years across, 100 trillion stars, one of the largest single galaxies known, is just one galaxy. And galaxies don't exist alone. Galaxies cluster together through gravity, forming structures of increasing scale. Our Milky Way belongs to a small collection called the local group. About 50 galaxies within a region, roughly 10 million light-years across. The two largest members are the Milky Way and Andromeda. Most of the others are dwarf galaxies, small companions orbiting one of the two large spirals. 10 million light-years. That's 100 times the diameter of the Milky Way. The local group is a structure where light takes 10 million years to cross from one side to the other. And it is considered a small galaxy group. Galaxy clusters are the next scale up. These are collections of hundreds to thousands of galaxies gravitationally bound together, with total masses of 100 trillion to more than a quadrillion solar masses. The largest member of a galaxy cluster is often a supergiant elliptical galaxy like IC1101, formed by the repeated merging of galaxies as they fall into the cluster's gravitational well. The Virgo cluster, the nearest major galaxy cluster to us, about 53 million light-years away, contains approximately 1,300 confirmed member galaxies and spans about 8 million light-years. Our local group is actually gravitationally influenced by the Virgo cluster, slowly falling toward it on a journey that has been underway for billions of years. The Coma cluster, about 321 million light-years away, is one of the closest examples of a truly rich galaxy cluster, containing over 1,000 galaxies within a region approximately 20 million light-years across. The total mass of the Coma cluster is estimated at about 7 quadrillion solar masses. Most of that mass, about 85%, is dark matter, the invisible substance whose nature remains one of physics' deepest mysteries. The hot gas that fills the space between galaxies and clusters, called the intra-cluster medium, is itself remarkable. It has temperatures of tens of millions to hundreds of millions of degrees. Heated by the gravitational energy released as matter fell into the cluster over billions of years. This gas emits X-rays, and in fact the X-ray emission from galaxy clusters is one of the primary ways we map the large-scale structure of the universe. The Coma cluster's intra-cluster medium has a total mass greater than all the stars in all its galaxies combined. But galaxy clusters, even the largest of them, are themselves clustered into even larger structures. Galaxy clusters group into superclusters, the largest structures in the universe that are gravitationally bound, meaning they're held together by their own gravity and won't be pulled apart by the expansion of the universe. Our local group belongs to the Virgo supercluster, also called the local supercluster. This structure contains the Virgo cluster as its gravitational center, along with at least 100 other galaxy groups and clusters arranged in a roughly flattened sheet, what astronomers call a filament or sheet of large-scale structure. The Virgo supercluster spans approximately 110 million light-years. 110 million light-years. Light crossing the Virgo supercluster from one side to the other takes 110 million years. 110 million years ago on Earth, the dinosaurs were in the middle of their dominance. The continents looked similar, but not identical to today. Flowering plants were newly evolved. Primates were 50 million years in the future. But in 2014, astronomers made a discovery that fundamentally changed how we understand our cosmic address. A team led by R. Brent Tully at the University of Hawaii used a new technique to map the large-scale structure of the universe around us by tracking the motions of galaxies, how they flow toward and away from regions of greater mass concentration. What they found was that the Virgo supercluster is not an independent structure. It is just one lobe of an enormous superstructure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, a vast region of space in which the gravitational influence of a central attractor, called the Great Attractor, draws galaxies into a coherent flow. Laniakea contains approximately 100,000 galaxies, has a total mass of about 100 quadrillion solar masses, and spans approximately 520 million light-years. 520 million light-years. That's 5,200 Milky Way diameters. Light crossing Laniakea from one edge to the other takes 520 million years. Longer than complex animal life has existed on Earth. The Cambrian explosion, when most major animal body plans appeared, was only about 540 million years ago. The Milky Way sits near the outer edge of Laniakea, in a relatively quiet region. The central attractor, the Great Attractor, is a region of enormous mass concentration, pulling all the galaxies in Laniakea toward it, including our own Milky Way. We are falling toward the Great Attractor right now, at hundreds of kilometers per second, pulled by the collective gravity of a structure 520 million light-years across. We'll never reach it. The expansion of the universe will prevent it. But we're moving in its direction. Laniakea was a revelation. It revealed that our cosmic neighborhood is far more structured and coherent than previously understood. But Laniakea is not itself the largest thing in the universe. It's one of many superclusters arranged in an even larger pattern. Zoom out far enough, far beyond individual galaxies, far beyond clusters, far beyond superclusters, and you see something extraordinary. The universe has a structure, not a random scattering of matter, not a uniform distribution, a network, a web. The cosmic web is the large-scale structure of the universe. The pattern in which all matter, visible and dark, is arranged at the largest observable scales. It consists of three types of structures: filaments, sheets, and voids. Filaments are long, thin strands of matter. Galaxies and dark matter arranged in thread-like structures that can extend hundreds of millions of light-years. They are the densest features of the cosmic web, the highways along which galaxies cluster and cluster more. Where filaments intersect, you find the densest nodes, galaxy superclusters and clusters, the most massive gravitational environments in the universe. Sheets are the two-dimensional structures that separate voids, great walls of galaxies arranged in flattened configurations that can span billions of light-years. And voids are the vast, nearly empty regions between the filaments and sheets. Bubbles of space containing very few galaxies, sometimes spanning hundreds of millions of light-years. The voids make up the majority of the universe's volume. The matter we can see, and the dark matter we can infer, occupies the filaments and sheets, which are relatively thin. Most of the universe, by volume, is nearly empty void. The cosmic web looks, at first glance, remarkably like something biological, like a neural network, like the interior structure of a cell, like the branching pattern of rivers or lightning. These resemblances are not coincidental. They reflect the fact that similar mathematical structures, networks, branching hierarchies, scale-free patterns, arise in many different physical systems. But the cosmic web is the largest such structure in existence, the largest connected pattern of matter in the observable universe. Simulations of cosmic evolution, massive computer programs running on supercomputers for weeks or months, produce cosmic webs that match what we observe with remarkable precision. These simulations start with the tiny quantum fluctuations in the early universe. Let gravity amplify them over 13.8 billion years and arrive at structures that look like the universe we actually see. This is one of the great triumphs of modern cosmology: the ability to simulate the entire large-scale structure of the observable universe from first principles. Within this cosmic web, some individual structures stand out for their sheer scale. These are the objects that we're building toward, the contenders for the title of largest thing in the universe. In 1989, astronomers Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics were mapping the positions of galaxies in a slice of the sky when they discovered something unexpected. There was a structure, a coherent arrangement of galaxies stretching across their entire survey, that they hadn't anticipated. They called it the Great Wall, also known as the CFA-2 Great Wall after the institution where it was discovered. The Great Wall is a sheet of galaxies, a filamentary structure in which galaxies are arranged in a roughly flat, elongated formation. It spans approximately 500 million light-years in length, 300 million light-years in width, and about 15 million light-years in thickness. It contains thousands of galaxies, and it was, at the time of discovery, the largest known structure in the observable universe. 500 million light-years. That number didn't quite register when it was announced. It was so much larger than anything previously mapped in 3 dimensions that astronomers initially questioned whether it could be real, whether the survey was perhaps somehow biased toward finding a pattern that wasn't truly there. But subsequent observations confirmed it. The Great Wall was real, and its discovery changed how cosmologists thought about large-scale structure. It raised a question that would only become more pressing as larger and larger structures were found. Is there a limit to how large cosmic structures can be? And if so, what is it? The answer to that question turns out to be one of the most profound and one of the most contested results in modern cosmology. But to get there, we need to continue up the scale ladder, because the Great Wall was only the beginning. In 2003, the Sloan Digital Sky Survey, a systematic mapping project that would ultimately catalog over 1 billion astronomical objects, revealed a new structure, the Sloan Great Wall. The Sloan Great Wall is a filament of galaxy clusters and superclusters stretching approximately 1.37 billion light-years in length, nearly 3 times larger than the original Great Wall. Located about 1 billion light-years from Earth, it's a coherent structure visible across a vast expanse of the survey area. 1.37 billion light-years. Let's sit with that for a moment. The Sun is 8 light-minutes from Earth. Alpha Centauri is 4.24 light-years away. The Milky Way is 100,000 light-years across. The distance to the Andromeda Galaxy is 2.5 million light-years. The Virgo cluster is 53 million light-years away. Laniakea spans 520 million light-years. The Sloan Great Wall is 1.37 billion light-years long. It's longer than the diameter of Laniakea. It's 13,700 times the diameter of the Milky Way. Light has been crossing it for 1.37 billion years, and it still hasn't reached the other end. It started crossing the Sloan Great Wall when the most complex life on Earth was single-celled organisms in shallow seas. Before even the Cambrian explosion, before animals, before plants, before any multicellular life. And yet the Sloan Great Wall, when it was discovered, was itself soon surpassed. The history of cosmological discovery in the 21st century has been, in one sense, a continuous discovery of structures larger than we thought the universe should contain. Each new survey maps a larger volume of space. Each larger volume reveals larger structures. And the theoretical limit, the scale above which structures shouldn't form, keeps being challenged. In 2016, astronomers analyzing data from the Baryon Oscillation Spectroscopic Survey, BOSS, announced the discovery of what was at the time the largest known structure in the observable universe. They called it the BOSS Great Wall. The BOSS Great Wall is a complex of superclusters and filaments spanning approximately 1 billion light-years in height, 1 billion light-years in width, and about 2 billion light-years in length. A three-dimensional structure of staggering size, containing several known superclusters, including parts of the Laniakea supercluster's neighborhood and other massive systems. But here is where something important needs to be said about structures at this scale. Something that creates genuine scientific tension. Cosmological theory, specifically the standard cosmological model, lambda-CDM, makes predictions about the largest structures that gravity can assemble over the 13.8 billion-year history of the universe. There is a theoretical maximum scale, called the scale of homogeneity, above which the universe should appear uniform. Matter should be roughly evenly distributed. No coherent structures should exist. That scale is approximately 300 to 400 million light-years, depending on how you define coherent structure and significantly non-uniform. The BOSS Great Wall is approximately 2 billion light-years long, more than 5 times larger than the theoretical maximum scale. Cosmologists debate how to interpret this. Some argue that the BOSS Great Wall, while physically present, is not a single gravitationally bound structure, that the galaxies in it are not actually more tightly connected to each other than to galaxies elsewhere, and that what we're calling a structure is really just a statistical fluctuation, a chance alignment that looks coherent, but isn't truly so in a dynamically meaningful sense. Others are less comfortable with that dismissal. They point out that the structures we observe at these scales are consistently larger than models predict, and that this might be telling us something important about dark energy, about the initial conditions of the universe, or about modifications to the standard cosmological model that we haven't yet accounted for. This tension between what we observe and what the standard model predicts is one of the most active frontiers in contemporary cosmology, and it only becomes more acute when we look at the largest structures discovered so far. We have arrived at the largest known structure in the observable universe, and it is, in the most precise scientific sense, a problem. The Hercules Corona Borealis Great Wall, named for the constellations in the direction where it was discovered, was first reported in 2013 and confirmed in subsequent studies. It is a concentration of gamma-ray bursts, the most energetic explosions in the universe, visible across billions of light years, that appear to cluster in a region of the sky in a non-random pattern. Gamma-ray bursts are used as tracers of large-scale structure because they're visible at enormous distances. Where there are more gamma-ray bursts concentrated in a region of the sky, there is more matter, more galaxies, more star formation, more massive stars dying in violent explosions that we can detect from billions of light years away. The Hercules Corona Borealis Great Wall, based on the distribution of gamma-ray bursts, appears to span approximately 10 billion light years. 10 billion light years. Let's make sure that number registers. The observable universe is approximately 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall is approximately 10 billion light-years across. It occupies roughly 1/9 of the diameter of the entire observable universe. This is not a structure that cosmologists expected to find. This is not a structure that the standard cosmological model comfortably accommodates. It is not merely large. It is a direct challenge to one of the foundational assumptions of modern cosmology: the cosmological principle. The cosmological principle states that the universe, on sufficiently large scales, is homogeneous, the same everywhere, and isotropic, the same in every direction. This is not just an aesthetic preference. It's a mathematical necessity for the standard equations of cosmology to work. If the universe is not homogeneous and isotropic at large enough scales, the equations we use to describe its evolution, the Friedmann equations, which underlie virtually all of modern cosmological theory, need to be modified or replaced. The expected scale of homogeneity, the scale above which the universe should look smooth and uniform, is somewhere between 300 and 400 million light years. Different measurements give slightly different values, but they're all in that general range. A structure 10 billion light years across is roughly 25 to 30 times larger than the scale of homogeneity. It shouldn't exist if the cosmological principle holds at the expected scale. 3 possible explanations are currently under discussion in the scientific community. The first is that the apparent structure is a statistical artifact. Gamma-ray burst detections are inherently rare events, and with a limited sample, random clustering can produce apparent patterns that don't represent true, large-scale density enhancements. The apparent wall might be a chance concentration that future surveys with more data will dissolve into background noise. This is the most conservative interpretation, and it's the one that requires the least modification to existing theory. The second is that the structure is real, but our understanding of what constitutes a gravitationally coherent structure at these scales is inadequate. Perhaps structures can form through mechanisms not fully captured in current simulations. Perhaps dark energy has properties we haven't correctly modeled. Perhaps the initial power spectrum of fluctuations from inflation has features at large scales that we've underestimated. In this case, the structure is real, but it doesn't necessarily break the cosmological principle. It just means our implementation of it needs refinement. The third and most radical interpretation is that the cosmological principle fails at this scale. That the universe is genuinely not homogeneous at scales of billions of light years. That the standard cosmological model, for all its successes, is missing something fundamental about how matter is organized at the largest scales. This would require a significant revision to the foundations of cosmology. New physics at large scales, modifications to our understanding of dark energy, or perhaps entirely new cosmological frameworks. We don't know which of these is correct. The Hercules Corona Borealis Great Wall is, as of now, an open problem. A structure whose existence challenges one of the pillars of our understanding of the cosmos. And the discomfort it creates in the cosmological community is genuine. We've been talking about the largest concentrations of matter, the filaments, walls, and superclusters where galaxies cluster. But there's another kind of extreme structure in the universe: the voids. Cosmic voids are the vast, nearly empty regions between the filaments and sheets of the cosmic web. They're not completely empty. They contain some galaxies, some gas, some dark matter. But their density is far below the cosmic average. While the filaments and walls contain perhaps 90% of all visible matter in the universe, voids make up approximately 80% of the universe's total volume. The largest known cosmic void is the Boötes void, also called the Great Void, discovered in 1981. It spans approximately 330 million light-years in diameter. Within that 330 million light-year sphere, there are almost no galaxies. A region of space larger than 3,300 Milky Way diameters, containing a handful of galaxies where there should be thousands. When it was first discovered, astronomers initially thought it might be an error, an artifact of incomplete sky surveys. But subsequent observations confirmed it. The Boötes void is genuinely, dramatically underdense, and its emptiness is itself a kind of record. It's the record for the emptiest region of space we've mapped in the observable universe. If you lived in a galaxy within the Boötes void, your night sky would be very different from ours. Looking outward in most directions, you'd see almost nothing. Your nearest galaxy neighbor might be 50 to 100 million light-years away. The cosmic web would be a distant horizon in every direction, a faint glow of clustered galaxies at the edges of the void, with the void itself filled only by the faint infrared glow of the cosmic microwave background, the afterglow of the Big Bang itself. There's something philosophically extraordinary about the voids. The cosmic web concentrates matter into filaments and sheets, leaving vast, empty spaces between them. Those empty spaces are not wasted space. They are essential to the structure. The voids define the filaments just as silence defines music. Without the voids, there would be no structure. Without structure, there would be no galaxies, no stars, no planets, no us. The largest empty space and the largest filled structures are complementary. They are two aspects of the same underlying pattern. The cosmic web that is the universe's large-scale skeleton. Now we arrive at something strange. An object, if you can call it that is simultaneously the largest thing we can observe and one of the most ancient. The cosmic microwave background, or CMB, is the thermal radiation left over from the epoch of recombination. The moment approximately 380,000 years after the Big Bang. when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was a hot, dense plasma opaque to light. After it, light could travel freely for the first time. The light released at the moment of recombination has been traveling through the universe ever since. As the universe expanded, this light was red-shifted, stretched to longer and longer wavelengths, until today it appears as microwave radiation with a temperature of approximately 2.725 Kelvin, just barely above absolute zero. This is the CMB. The CMB is not located in one place. It surrounds us completely, from every direction, at the same distance. The distance light has traveled since 380,000 years after the Big Bang. It is a sphere centered on us with a radius of approximately 45 billion light years. That's the observable universe's edge, as seen in the CMB. In a physical sense, the CMB represents a surface, the last scattering surface, the boundary of what we can see with electromagnetic radiation. Beyond it, the universe is opaque. The CMB is our cosmic horizon, and it's not perfectly uniform. Tiny temperature fluctuations, variations of about 1 part in 100,000, pattern the CMB across the entire sky. These fluctuations are the seeds of all large-scale structure. The slightly denser regions in the CMB were the proto-seeds of galaxy clusters. The slightly underdense regions became voids. Everything we've discussed tonight, every galaxy, every cluster, every supercluster, every filament, every wall, grew from the tiny quantum fluctuations encoded in the CMB 380,000 years after the Big Bang. The CMB is simultaneously the largest thing we can observe. It surrounds us at the edge of the observable universe. And the oldest snapshot of the universe we have access to, showing us the cosmos as it was 380,000 years after the Big Bang, 13.4 billion years ago. It's the largest, oldest map of the universe's initial conditions. And it explains how everything else in tonight's list came to be. We've reached the top, the largest structure we can define, the largest thing that in any coherent sense contains everything else we've discussed. The observable universe is a sphere approximately 93 billion light-years in diameter, centered on Earth, or more precisely, on any observer. Since every observer at any location would see themselves at the center of their own observable universe, with the same horizon at approximately 46 billion light-years in all directions. The universe is 13.8 billion years old. Why is the observable universe 93 billion light-years across, rather than 27.6 billion light-years, 13.8 billion years times 2? Because the universe has been expanding throughout its history. The most distant regions we can observe, regions whose light has been traveling toward us for 13.8 billion years, have themselves moved away from us during that time due to the expansion of space. When you account for the expansion, the co-moving distance to the edge of the observable universe is approximately 46 billion light-years in any direction. Within the observable universe, there are an estimated 2 trillion galaxies. Not 200 billion, the older estimate, 2 trillion. A 2017 study using data from the Hubble Space Telescope concluded that previous estimates had missed the vast majority of small, faint galaxies at high redshift, and that the true number is at least 10 times higher than previously thought. 2 trillion galaxies. If each galaxy has an average of 100 billion stars, a conservative estimate, many large galaxies have far more. The observable universe contains approximately 2 times 10 to the 23rd power stars. That's 200 quintillion stars. More stars than there are grains of sand on all the beaches and deserts of Earth by a factor of millions. And the observable universe is almost certainly not all there is. Current evidence suggests the total universe extends far beyond the observable boundary, possibly infinitely. The observable universe is the part we can see from our location. It's not the entirety of what exists. Other regions, equally real, equally vast, lie beyond our horizon, forever inaccessible because the light from them has not yet reached us. And in many cases, due to the accelerating expansion of the universe, never will. Before we talk about the expanding universe, we need to talk about what sits at the center of the largest galaxies we've described. Because the black holes at the hearts of the biggest galaxies are themselves record breakers. Every large galaxy is now understood to harbor a supermassive black hole at its center. This is not a speculation. It's confirmed by decades of observations. The Milky Way has Sagittarius A star with a mass of 4 million solar masses. Andromeda has a black hole of approximately 100 million solar masses. The black hole at the center of the giant elliptical galaxy M87, the first black hole ever directly imaged by the Event Horizon Telescope in 2019, has a mass of approximately 6.5 billion solar masses. 6.5 billion solar masses. That number needs to be understood carefully. Our Sun has been converting hydrogen to helium for 4.6 billion years at a rate of 600 million tons per second. A black hole with 6.5 billion times that mass is an object so dense that light cannot escape from within it. A region of space-time so curved that no known force can push matter back out once it crosses the event horizon. With an event horizon diameter of approximately 120 billion kilometers, larger than the distance from the Sun to Pluto's orbit by a factor of several. But M87's black hole is not the largest known, not even close. TON 618 is a quasar, an actively feeding supermassive black hole located approximately 10.4 billion light-years from Earth. Its black hole has an estimated mass of 66 billion solar masses. Its event horizon has a diameter of approximately 1.3 trillion kilometers. The entire solar system, from the Sun to the orbit of Neptune, would fit inside TON 618's event horizon with room to spare. Light crossing the event horizon from one side to the other would take approximately 40 days. Holm 15, a star, the central black hole of the galaxy, Holm 15A in the Violates 5 cluster, has a mass estimated at approximately 40 billion solar masses, making it one of the most massive known black holes with a direct mass measurement rather than an inferred one. These ultramassive black holes, defined as black holes with masses exceeding 10 billion solar masses, are the most massive single objects in the universe. They are not made of any familiar substance. They are regions of space-time where the density of matter that originally formed them exceeded the limit at which any known force can provide support against further collapse. They are the ultimate endpoint of matter compression. Objects whose gravity is so strong that they alter the fabric of space-time around them significantly enough to be detected through their effects on orbiting stars and gas, and through the images of their shadows captured by telescope networks the size of the Earth. The relationship between galaxies and their central black holes is one of the most active areas of astronomical research. The masses of supermassive black holes correlate remarkably well with properties of their host galaxies, especially the mass and velocity dispersion of the central stellar bulge. This correlation, called the M-sigma relation, implies that galaxies and their black holes co-evolved, growing together over billions of years through complex feedback mechanisms that we're still working to fully understand. When a supermassive black hole is actively accreting matter, when gas is falling into it from the surrounding galaxy, the energy released is enormous. The accretion disk around the black hole heats to millions of degrees, emitting radiation across all frequencies. Relativistic jets, beams of matter and energy moving at close to the speed of light, can be launched from the poles, extending thousands of light years into the surrounding galaxy and beyond. This active phase is what produces quasars, the most luminous, continuous sources of electromagnetic radiation in the universe. And here's something remarkable about quasar luminosity. At its peak, a quasar like TON 618 outshines its entire host galaxy by a factor of hundreds to thousands. A single black hole consuming matter at the center of a galaxy produces more light than hundreds of billions of stars combined. The energy comes not from nuclear fusion, but from gravity, from the release of gravitational potential energy as matter falls into the deep gravitational well of the black hole. Gravity, the weakest of the fundamental forces at small scales, becomes the most powerful energy source in the universe at astronomical scales. These monsters, the ultramassive black holes at the hearts of the largest galaxies, are not incidental features of the cosmic landscape. They are active participants in the formation and evolution of galaxies. They heat the gas in their host galaxies, suppressing star formation when they're active. They launch jets that can prevent gas in galaxy clusters from cooling and forming new stars. They regulate the growth of galaxies by essentially limiting how much cold gas can accumulate. The largest galaxies in the universe, the supergiant ellipticals like HC 1101, grew to their enormous sizes partly through a complex dance with the ultramassive black holes at their centers. The largest single objects in the universe are not stars. They are not even galaxies. The largest single objects, by mass, are the ultramassive black holes, invisible to direct observation, but revealing themselves through their gravitational influence on everything around them. The largest things that exist are, paradoxically, defined by the absence of anything inside their event horizons. They are singularities, or perhaps something else, something we don't yet have the physics to describe, surrounded by a boundary from which nothing returns. We mentioned the great attractor earlier when discussing La Niaikea. Now let's understand it more fully, because it represents one of the most dramatic manifestations of large-scale structure. A gravitational anomaly that has been reshaping the distribution of galaxies across hundreds of millions of light years for billions of years. The Great Attractor is not a single object. It's a region of space with an unusually high concentration of mass, galaxies, clusters, dark matter, that creates a gravitational pull felt across an enormous volume. Our Milky Way, along with the entire local group, is being pulled toward the Great Attractor at approximately 600 kilometers per second. Millions of galaxies across the Laniakea supercluster are similarly falling inward. Identifying the Great Attractor was difficult because it lies in the zone of avoidance, the region of the sky obscured by the dust and stars of the Milky Way's own disk. For decades, the Great Attractor was known only through its gravitational effects. Only with radio and X-ray observations that can penetrate the obscuring dust did astronomers begin to map what's actually there. What's there turns out to be the Norma cluster, a massive galaxy cluster, along with several other concentrations of mass, all forming part of the Hydra Centaurus supercluster. The total mass of the Great Attractor region is estimated at approximately a quadrillion solar masses. But even the Great Attractor doesn't tell the whole story of what's pulling us. More recent surveys revealed an even larger structure behind it. The Shapley supercluster, located about 650 million light-years away, which is itself one of the largest concentrations of matter in the observable universe, and exerts a gravitational pull on our region of space that exceeds that of the Great Attractor. We are, in other words, embedded in a gravitational landscape that extends for hundreds of millions of light-years in every direction. The motions of galaxies across Laniakea, including our own, reflect the combined gravitational influence of the Great Attractor, the Shapley supercluster, and dozens of other mass concentrations. We are not floating freely. We are being pulled, attracted, shaped by the gravitational influence of structures we cannot even fully see. And we're not moving toward these attractors alone. Every galaxy in Laniakea is being pulled along similar trajectories. The entire supercluster is slowly, over billions of years, flowing inward toward its center. Eventually, in the far future, the inner parts of Laniakea may merge into a single, enormous structure, unless dark energy accelerates fast enough to overcome the attraction first. This tension between gravitational attraction and dark energy repulsion defines the fate of every structure we've discussed tonight. On small scales, within galaxies, within clusters, gravity wins. These structures are bound and will persist. On large scales, between superclusters, the dark energy wins. These structures will be pulled apart. The cosmic web, already at its maximum development, is slowly being dissolved by the accelerating expansion of the universe. The largest things that exist today are as large as they will ever get. They are at their peak right now, in this epoch of the universe's history. In the far future, there will be no structures at the scale of the Hercules Corona Borealis Great Wall. There will be no cosmic web. There will be isolated islands of matter, galaxies or galaxy groups, separated from each other by an ever-expanding void. We live at the moment of maximum cosmic structure. The universe will never again be as organized, as richly patterned, as full of the hierarchy of structures we've described tonight as it is right now. Everything we've described tonight is embedded in a universe that is not static. It's expanding, And not just expanding at an accelerating rate. In 1929, Edwin Hubble confirmed what had been theoretically predicted by Georges Lemaitre. The universe is expanding. Distant galaxies are receding from us. The farther they are, the faster they're moving away. This is Hubble's law, and it's one of the most fundamental observational facts in cosmology. For most of the 20th century, cosmologists assumed that while the universe was expanding, gravity from all the matter in it would be gradually slowing that expansion. Like a ball thrown upward, moving, but decelerating. The question was whether there was enough matter for gravity to eventually halt and reverse the expansion, or whether the universe would expand forever, but at a decreasing rate. In 1998, two independent teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, made a discovery that earned the 2011 Nobel Prize in Physics. They were using Type 1a supernovae as standard candles to measure cosmic distances, and what they found upended everything. The expansion of the universe is not slowing down. It's speeding up. Distant supernovae are dimmer than they should be if the expansion were decelerating. They're farther away than expected. The universe is expanding faster now than it was in the past, and that acceleration is increasing over time. The cause of this acceleration, whatever it is, has been named dark energy. It comprises approximately 68% of the total energy content of the universe. Combined with dark matter at 27%, ordinary matter, everything you can see and touch and detect directly, every star, every planet, every galaxy, every atom in every human being, makes up only about 5% of the universe. Dark energy is the most perplexing quantity in physics. It is measured with high precision. We know how much of it there is and how it behaves. It acts like a constant energy density of empty space, present everywhere uniformly. But we have essentially no idea what it is. The best theoretical prediction for dark energy from quantum field theory, the vacuum energy of empty space, comes out 10 to the power of 120 times larger than what we observe. That discrepancy of 120 orders of magnitude is the largest mismatch between theory and observation in the history of science. It's called the cosmological constant problem, and it remains completely unsolved. What dark energy means for the future of cosmic structures is clear. As time goes on, the accelerating expansion pushes everything apart. Gravitationally bound structures, individual galaxies, clusters, superclusters, remain intact because their internal gravity is strong enough to hold them together against the expansion. But on the largest scales, the cosmic web is gradually dissolving. The voids are growing. The filaments are thinning. The structures we've been discussing are at their peak now. They will never be larger than they are today, because dark energy is working against further growth. Eventually, in a far future universe, even clusters of galaxies will be gravitationally separated from each other by the expansion. Galaxies will be alone in an expanding void. Stars will die. The lights will go out. But that's a story for another night. We've described the structures. Now let's understand how they formed, because the process itself is one of the most extraordinary stories in physics. It starts with quantum mechanics. In the very early universe, fractions of a second after the Big Bang, the universe was an extraordinarily hot, dense, tiny region of space. Within that tiny region, quantum mechanical fluctuations, the fundamental uncertainty at the heart of quantum physics, created tiny variations in density. Some regions had slightly more matter than average, some had slightly less. During a period called inflation, an extraordinarily rapid expansion of space that happened in the universe's first tiny fraction of a second, these tiny quantum fluctuations were stretched to cosmic scales. What were fluctuations on the scale of subatomic particles became fluctuations on scales that would eventually become galaxy clusters and superclusters. Inflation took the smallest possible variations and stamped them onto the universe at every scale. After inflation ended, the universe continued to expand, cool, and evolve. The slightly overdense regions had slightly more gravity. That slightly stronger gravity pulled in surrounding matter. More matter meant more gravity. More gravity pulled in still more matter. This process, gravitational collapse, progressively amplified over billions of years, is what built the cosmic web. The process is exquisitely sensitive to the initial conditions. Small variations in the overdensities from inflation produce large differences in the structures that eventually form. Simulate the universe with slightly different initial conditions, and you get a different cosmic web. Different filaments, different voids, different cluster locations. The fact that our simulations of cosmic structure formation, starting from the CMB fluctuations and running forward 13.8 billion years, produce a cosmic web that matches our observations is one of the most impressive achievements of modern science. It tells us that we understand the broad physics of how the universe organized itself at large scales. Gravity, dark matter, dark energy, and the initial conditions from inflation are sufficient to explain the filaments, sheets, clusters, and voids we observe. What they may not fully explain, and this is the crux of the problem posed by the Hercules Corona Borealis Great Wall, are the very largest structures. At scales of billions of light years, the Standard Model's predictions may be breaking down. The largest things in the universe may be telling us that our current understanding is incomplete. We've climbed the entire ladder, from the red hypergiant stars with diameters billions of kilometers wide, to the nebulae spanning hundreds of light years, to globular clusters and galaxies, to superclusters spanning hundreds of millions of light years, to the cosmic web and its great walls, to the Hercules Corona Borealis Great Wall at 10 billion light years, to the observable universe itself at 93 billion light years. What does any of this mean? The first thing it means is that we are extraordinarily small, not in any way that diminishes us. Smallness in a physical sense carries no implication about significance. But the raw fact of our scale relative to the structures we've discussed tonight is worth sitting with. The largest thing we can observe, the observable universe, is roughly 10 to the 27th power times larger than a human being, a 1 followed by 27 zeros. If you wrote out that ratio in full, if you tried to represent the relationship between your body and the observable universe numerically, the number would have 27 digits. The second thing it means is that we live inside a universe with structure at every scale. From quantum fluctuations to atoms, to cells, to organisms, to mountains, to planets, to stars, to galaxies, to superclusters, to the cosmic web. At each scale, matter is organized. At each scale, the organization of matter at smaller scales creates the building blocks for organization at larger scales. Atoms make molecules. Molecules make cells. Cells make organisms. Organisms shape planets. Stars shape galaxies. Galaxies shape the cosmic web. We are not separate from the cosmic web. We are a part of it, a particular, local, temporary expression of the same organizational process that created the filaments and voids. The same gravity that pulls galaxies into clusters pulled the matter that became you out of the interstellar medium and into a star, and from that star into a planetary disk, and from that disk into a planet, and from that planet into you. The third thing it means is that our models, our best current understanding of how the universe works, may be incomplete at the largest scales. The Hercules Corona Borealis Great Wall challenges our standard cosmological model in a way that hasn't been resolved. And that's important. Not as a reason to distrust science, but as a reminder of what science actually is. A process of building the best possible models of reality, recognizing their limitations, and improving them when new observations reveal those limitations. Every time in the history of physics that a model failed to explain a new observation, that failure eventually led to a deeper understanding. Newtonian gravity couldn't explain the perihelion precession of Mercury, until general relativity explained it and revealed a deeper description of space-time. The black-body radiation spectrum couldn't be explained by classical physics, until quantum mechanics explained it and revealed an entirely new layer of physical reality. The anomalous rotation of galaxies couldn't be explained by visible matter, until dark matter became the standard explanation and revealed that most of the universe is made of something we can't see. The Hercules Corona Borealis Great Wall might be the next of these failures. The observation that pushes us toward a deeper theory. Or it might dissolve with more data, a statistical artifact that disappears when we map more of the sky. We don't know yet. But the not knowing is not a failure. It's an invitation. Let's end on the deepest question that tonight's subject raises. We've established that the observable universe is approximately 93 billion light-years in diameter. We've established that within it, structures exist that are 10 billion light-years across. And we've established that the total universe, beyond the observable boundary, is almost certainly much larger, possibly infinitely larger. If the universe is infinite, then the structures we've described are not the largest things that exist. They're just the largest things we can see. In an infinite universe, there is no upper limit to the size of structures. There could be structures 1 trillion light-years across, a quadrillion, arbitrarily large, as long as there's enough space for them to form. But there's something even stranger. In an infinite universe with any non-zero density of matter, the universe is not just large, it's repetitive. The number of possible arrangements of matter in any finite volume is finite. In an infinite universe with infinitely many such volumes, every possible arrangement of matter must occur, and must occur infinitely many times. This means that in an infinite universe, there are infinitely many regions that look exactly like our observable universe. Infinitely many Milky Ways, infinitely many Earths, infinitely many copies of every person alive, including you. An infinite number of yous distributed across an infinite universe, each living in a region indistinguishable from yours. This is not science fiction. This follows directly from the mathematics of an infinite homogeneous universe. A universe where matter is roughly evenly distributed on the largest scales. Cosmologist Max Tegmark has calculated that the nearest exact copy of you, if the universe is infinite and roughly homogeneous, would be approximately 10 to the power of 10 to the power of 29 meters away. A number so vast it makes the observable universe seem like a single atom. Whether the universe is actually infinite, whether this bizarre consequence is physically real, is unknown. We have no way to observe beyond the cosmic horizon. The CMB gives us our earliest snapshot of the observable universe, but tells us nothing about what lies beyond. The universe might be infinite. It might be finite and curved, wrapping back on itself like the surface of a sphere but in 4 dimensions. We don't know. What we do know is that the structures we can see, the ones we've cataloged tonight, already strain the capacity of any human mind to truly grasp. The Hercules Corona Borealis Great Wall at 10 billion light-years is already so large that our best cosmological models struggle to explain its existence. If the universe extends vastly beyond what we can see, the structures within it might make even that pale in comparison. We live at the edge of knowledge, looking outward with instruments that have only recently become powerful enough to map these scales, finding things larger than our models predict, confronting the possibility that the universe is organized at the largest scales in ways we don't yet understand. And the extraordinary thing, the thing that should fill you with something other than vertigo, is that we found all of this. We, a species that emerged from the African savanna perhaps 300,000 years ago, that built cities only 10,000 years ago, that flew for the first time only 120 years ago. We built instruments sensitive enough to detect the afterglow of the Big Bang from 13.8 billion years ago. We developed mathematics powerful enough to simulate the formation of the cosmic web. We wrote computer programs that model the evolution of the entire observable universe. We found a structure 10 billion light-years across and recognized that it shouldn't exist according to our current best theory. We found it, we named it, and now we're working on understanding it. That's what we do. That's what we are. The part of the universe that maps the universe, that holds up a mirror to the cosmos and says, "We see you, we're trying to understand you, and we're not done yet." Tonight, we started with you. One human being, 1.5 to 2 meters tall, and we worked our way up through stars and nebulae, through galaxies and clusters, through superclusters and the cosmic web, through great walls and voids, through the observable universe itself and the mysteries beyond it. And now we come back to you. You are made of approximately 7 times 10 to the 27th power atoms. That's 7 followed by 27 zeros. More atoms than there are stars in the observable universe, many times more. The atoms in your body are not simple. They're organized into molecules. Molecules into proteins, proteins into cells, cells into tissues, tissues into organs, organs into you. The information content of that organization, the complexity encoded in your biology, your neurology, your particular history of experience and thought, is staggeringly large. You are, in terms of organized complexity, one of the most complicated things in the observable universe. perhaps the most complicated thing in a particular region of it. The cosmic web is large. The Hercules Corona Borealis Great Wall is unimaginably vast. The observable universe contains 2 trillion galaxies and 10 to the 23rd power stars. But the universe is mostly hydrogen, mostly simple, mostly unstructured by the standards of biology. The vast majority of the universe's volume is empty void. The vast majority of its matter is dark matter and hot plasma. Life, organized, self-replicating, information processing, aware life, occupies an extraordinarily small fraction of the universe by volume or mass. And yet, here you are, in that tiny fraction, aware of the rest. The largest things in the universe don't know they exist. The Hercules Corona Borealis Great Wall, a structure 10 billion light-years across, containing billions of galaxies, has no awareness of itself. It doesn't know it's large. It doesn't know it challenges cosmological models. It doesn't know it exists. You do. You know about it. You just spent this time learning its scale, its nature, its implications. You, a collection of organized matter 1.7 meters tall on a rocky planet orbiting a middle-aged star in a secondary spiral arm of a mid-sized galaxy. You know about a structure 10 billion light-years across that may challenge the foundations of cosmology. That is perhaps the most remarkable thing about scale. Not the scale of the large things, but the scale of the small thing that comprehends the large things. The universe has been organizing matter for 13.8 billion years. It built galaxies and clusters and superclusters and great walls. And somewhere in that process, in one small corner of one ordinary galaxy, it organized matter into something that could look outward and understand what it was seeing. That's you. That's us. That's what tonight was about. The largest things in the universe are extraordinary. But the fact that something small enough to hold in your hand can know about them, that's the most extraordinary thing of all. Sleep well tonight, in the smallest corner of the largest universe that has ever existed. A note on scale, one final comparison. Before we truly close, I want to give you one last comparison. Not to overwhelm, you've absorbed enough tonight, but to make the whole ladder concrete in a single image. Imagine you are standing in the middle of a vast, empty plain. You place a single atom on the ground in front of you. That atom represents you, a human being, roughly 2 meters tall, relative to the atom you've just placed. Now step back. Keep stepping back until the atom looks like a grain of sand. That grain of sand represents the Earth relative to the Sun. Keep stepping back until the grain of sand looks like a speck. That speck represents the solar system relative to the distance to Alpha Centauri. Keep stepping back. The speck becomes invisible. At that scale, the distance to Alpha Centauri is a single step. The Milky Way is a football field. The local group is a city block at this scale. The Virgo cluster is a small country. Laniakea is a continent. The observable universe, at this scale, is the entire surface of the Earth. And the Hercules Corona Borealis Great Wall, the largest known structure, covers roughly 1/9 of that surface. That is the scale we discussed tonight. That is the universe in which you live. A universe where the largest structures are continental in the language of a metaphor that is itself impossibly compressed from the actual mathematics. And to you, the atom we placed at the beginning, Know all of this. That, ultimately, is the point.